Hello guys, my name is Nandivardhan Reddy from Informational Technology, bearing roll number of 20951A1248. Today, subject is operating systems. In that, we are going to learn about a distributed deadlock detection and resolution algorithm for process network. Let's dive into the topic. The process, the process network (PN) model was introduced by Kohn in 1974. It is a data flow model in which concurrent processes communicate only over FIFO queue channels, first in, first out channels, queue channels. Process network naturally model functional parallelism and can model data parallelism. They, way, they are well suited for modeling signal processing systems, including parallel and distributed systems. It has widely been observed that concurrent and distributed programming is difficult. The formal underpinning of PN are a potential aid to easing this difficulty. A process network is represented as a direct graph, whereas each node represents a process and each arc represents a queue channel directed from producer to consumer. This model is natural for describing the streams of data samples in a single signal processing system. Typically, a system block diagram can naturally map one onto a process network. Common process network. Common process. The process network model in which multiple current processes and are connected via unidirectional first in first out queues to form a network. Each process may have any number of incoming or outgoing queues and may communicate to other processes only via these queues. Khan showed that a process network program is determined. The results produced on all queues are the same for every possible execution order, including concrete execution. PN uses simple local rules for scheduling and is therefore distributable and scalable. A node suspends execution when it attempts to read from an empty queue. When writing to a queue, a node can never be suspended. Here, queue can become infinitely long. A node cannot check for the presence of data on the queue, nor can it read from the more than one queue at a time. Infinitely large queues are undesirable, as execution in bounded memory is necessary for any partial implementation. Termination and total stream lengths are properties of the program and do not depend on the execution order of the nodes in the network. However, the number of unconsumed samples that can accumulate on queues does not depend on the execution order. Parks bounded scheduling. Parks bounded scheduling is scheduling policy to yield a bounded execution of an PN. If it is a possible, because it is undecidable whether a PN can be scheduled in bounded memory. The scheduler must work dynamically as the program executes. Parks policy depends suspends a node from for waiting to a full queue. If a queue is chosen to be too small, artificial deadlocks processes permanently blocked on the full queue. Make sure that we are not present in the original unbounded PN. Parks proposed a global dynamic deadlock detector that increases the size of the smallest block for full queue. Although counterexamples to Park's bounded scheduling policy eventually surfaced, his work was a major step towards making the model more than an academic curiosity. Gleanin and Bastian. Gleanin and Bastian further examined bounded scheduling of PN and introduced an additional requirement that the PN be effective. They can they call a PN effective only if every token that is proposed on a queue is eventually consumed. Bounded scheduling of an non-effective PN. may result in an incomplete execution. That is, execution may terminate earlier than it would have it in the unbounded model. Unfortunately, it is undecadable in general whether a PN is effective. Gainin and Bastian also showed that a dynamic deadlock detector should detect local deadlocks, not only global ones, as proposed by Fox. If the process is blocked, reading from an empty queue or writing to a full queue, it is dependent on the queue, unique other process. That at the other end of the queue, the only other resolution is to increase the size of blocked full queue because only blocked process depends on some unique other process. This gives rise to chains of dependencies. If the dependency chain is cyclic, it indicates a local deadlock and no further progress can be made without an external resolution. By detecting and resolving local deadlock, we can execute bounded effective PNs to completion in bounded memory. It is impossible to schedule all PNs in bounded memory. However, this is a very large set of PNs and arguably the most interesting set for practical applications. This is the okay dynamic deadlock detection. Proper bounded memory scheduling of PN requires dynamic detection of local deadlocks. If the detected deadlocks is artificial, then it must be resolved in order to preserve the determinacy of the PN. We present an algorithm that performs distributed dynamic deadlock detection and resolution D4R. D4R means distributed dynamic deadlock detection and resolution. Wilson and Evans presented an application of an algorithm by Michael and Merritt to deadlock detection of per PN. Although originally designed for distributed database applications, this Mitchell and Merritt algorithm appropriately detects deadlocks for PN. We present an algorithm based on a different Michael and Merritt algorithm for the same paper. The second algorithm uses process priorities and identifies the lowest priority process in the deadlock cycle so that it can be resolved. We assign the process properties such as that algorithm determines whether a deadlock is real or artificial and identifies the node that it is blocked right into the queue, which must be lengthened in order to resolve the deadlock. Okay, this is about using the same nodes and edges as in the PN graph. We can construct a weight for graph for the D4R algorithm. Here, an edge indicates that a process is blocked and waiting on a single other process. The directions of the wait for edges are from the waiting process to the process being waited on. Note that the edge in the wait for graph coincide with the edge in the original PN graph. For read blocked node, the direction of the edge is opposite. That's in the original graph. For our vision of the algorithm, each node contains algorithmic state data as shown, consisting of public and private sets of a triple, a non-decreasing counter count, a unique node identifier nodal ID, and a queue sized variable queue size, which serves the function of Mitchell and Merritt's priority variable. Each process is initialized with a public and private set equal. The public set changes as the algorithm progresses, but the private set remains unique to the node. Overall, the conclusion is process network (PN) are useful for modeling signal processing systems of streaming data and naturally captures parallelism in the system. Bounded effective process network can be executed in bounded memory, but require dynamic deadlock detection and resolution. We present the first algorithm to not only detect deadlock, but to determine whether it is real or artificial. And to resolve it, the distributed algorithm permits correct scheduling of bounded PN process network. Okay, this is about this topic. We'll end this session. Thank you.